At this point, all we've done is define what omega is.
Okay.
We haven't actually used it yet, but we're going to
Yeah,
use it here.
that was what my question is. Now we're going to go back to that problem.
Right, now we're going to go ahead, now that we know what this omega is, we're going to calculate it for this. And then we're going to use it here to find out what the voltage is at a particular time. Okay, so let's go ahead and get rid of the blue stuff here, since that's really just preliminary information. We have what we needed to extract out of it, which is those formulas there. Unfortunately, the information in the original problem is given differently, because it's given as a period, it's not given as a frequency. So the very first thing we're going to need to do is determine what F is in order to have a frequency that we can plug into this equation.
F equals 1 over time.
F is equal to 1 over t, which means we can replace here F with 1 over t and say that omega is equal to 2 pi divided by t. Right? 2 pi times 1 over t gives me 2 pi over t, which would therefore be equal to 6.28 divided by 1 millisecond, 0.001. So we move the decimal point 1, 2, 3 places, and we come up with 6,280 radians per second. Okay, so 1,000 pi. Think about it this way: each trip around is 2 pi, right? And we do 1,000 trips. So 2 pi times 1,000 is 6.28 times 1,000, or 6,280. Makes perfect sense, right? Maybe. Okay, so what now? We're going to multiply omega times t. Think about this. Omega has to do with an angular frequency. In other words, there's a velocity here. So after a certain amount of time, will be at a certain point. And as we go around that circle 1,000 times per second, somewhere along the line, if we click stop, we're going to freeze that radius somewhere in that circle. And that's what we want to find out. We want to find out as we go through that circle over time, and we freeze that action at some point, say right here, at a certain given time, that we could ultimately calculate what the actual voltage is going to be at that time. Okay, using this idea. We can also, if we wanted to, calculate when the output is equal to 0. Every 500 microseconds, the output is equal to 0. Every half a period. the output is equal to 0. But based on this 78-degree offset, we can't just say it happens at 500, it happens at whatever. And that 78-degree offset is a different amount of voltage change for any varying frequency. That's why we have to include that in our calculations. Okay? So we're never going to do any of these problems. There's no reason to do any of these problems for us. It's in the book. The book goes through doing these problems. What we want to extract out of this whole discussion is really very simple. And that is that there are more than one way, or there is more than one way, to represent a sine wave. Okay? In our world, what we will be extracting out of this is something that looks like this here. These represent the same waveform. .07 being, of course, the RMS value. And this minus 78 degree representing the angle. Any questions so far? You see where the 7.07 came from? Okay, so you know I may represent on a test or a quiz, I may represent a source this way, and you may see it represented that way in other places. You'll see it represented that way in a few chapters in your textbooks, but only the parts of your textbooks that concern themselves with needing to know that information. In our world, we don't generally need to know that information. There are occasions where we might want to know when the voltage is going to be equal to 0, because normally, in some cases, we like to turn things on or energize things when the voltage is equal to 0 so that it doesn't get a shock of all of a sudden being connected to a high voltage because it's happening somewhere in the waveform that's not equal to 0. If we connect that to something and it just happens to be at its peak at the time we make that connection, then whatever it is that we're sourcing with that energy is going to get slammed with 120 volts, or in this case 10 volts peak maximum voltage right off the bat, and that can cause equipment to fail prematurely. Causes premature wear on components. So in some cases we might want to start a motor or start something at a 0 voltage, but that doesn't really happen very often in our world. It happens more often in the electronics, strict electronics world, where they work within times down to the microsecond and millisecond. When you're talking about industrial machinery and power, you're not generally working down at that finite that small of a resolution. Okay, of course there are exceptions to every rule, and if you find yourself in one of those exceptions, then at least you'll know where that information is in your book, and you can review it. But really, it's just a question of plugging numbers into that equation. The sticky wicket in doing that is that we have radians here, we have degrees here, so you have to kind of do some funky things with your calculator to get it to do the calculation properly. So that's why we don't worry ourselves about it. It's kind of too much of a pain for the amount of usefulness that you would get out of getting it done. But if you want to figure out how to do it, feel free. Okay, you guys have a quiz coming up, I think, in a couple of days. Am I right?
Okay.
Please Tomorrow.
What's that?
I think it's tomorrow.
Is it tomorrow? Yeah. What's it on? What's on the quiz?
I want to say actuators.
Oh, that one. Well, that's 135 I'm talking about. We're not in 135 right now.
I'm trying to remember the other one.
We're in 120 right now. Let me have a look.
Didn't look at that one. So,
It seems to me we have something coming up. Day 10, quiz on AC waveform parameters. I just want to have a look at it and make sure that we've covered everything.
okay, that would be good.
Okay. You will, let's see, the most robust thing that you're going to have to do, let's see, here's what you're going to have to be able to do. Calculate sines and cosines. Reactance is x sub c and x sub l. What else? Add, subtract, multiply, divide, complex numbers. Okay, we're talking about the, 3 at an angle of 12 times 4 plus j8. Something along those lines. Have to convert this to,
Yeah, because it's multiplication, it's got to go to polar.
yeah, so we'd have to convert that to polar, do our multiplication, and then you can give me the answer. And I don't normally ask for the answer in any particular version, so if you want to give it to me in polar, give it to me in rectangular, it doesn't really make any difference. You have to be able to do the conversions. And there are just some questions on here that are just, convert 35 and 60 to rectangular form, that sort of thing. There are 2 problems at the end, and they are impedance problems. Something like this. X sub L is equal to 16 ohms. R is equal to 12 ohms. What is Z? You should have the answer already written down. Should have taken you about 4 seconds to write down that answer. Do you have it written down? How about 12 plus J16? Twelve ohms of resistance, 16 ohms of inductance. Remember, on our axes are X sub L, X sub C. Remember? You looked at that.
Okay, so if it was capacitor, it'd be 12 minus J 16.
That's correct.
Okay.
Okay, so I'm going to ask you to tell me what the impedance of that circuit is. It won't be, obviously, it's not going to be this exact circuit, but one that's similar.
And impedance is Z.
Z is impedance, which is, in this case, since it's a series circuit, is the sum of the two, because they're in series. That's what gave us license to add these two together, is because they're in series. We wouldn't be able to do that if they were in parallel. But that's another quiz for another day. All right, so jot that down if you have any questions. That's pretty much what's going to be on the quiz. There'll be AC waveform parameters will be on there too, being able to determine if you know what peak is and peak to peak and RMS, those calculations, period to frequency calculations will be on there. I don't think there's anything about omega or what we talked about today on there, however, so that shouldn't be a problem. It's pretty much what we have here in the AC waveform stuff. Okay? Questions? All right, good deal.